Alright, suppose we have a prime ideal P, and we have the natural ring homomorphism, which sends an element A to A over 1. This is how we can naturally embed a ring A in the field of fractions, or the ring of fractions. Alright, so for any n greater than or equal to 1, let Qn be the ideal generated by P to the n. So P to the n is just all elements. This is obviously just going to be product from 1 to n of pi, where each pi is contained in the ideal P. And we want to prove that the inverse image under this natural map is primary. What does it mean to be primary? That means that it's sort of like prime, but in prime, if you have a product which is contained in the ring, then if one element is not in the product, then the other element is, so AB in Q, if you have a primary ideal A, then the product AB is in the ideal A. If this holds, and if A is not in A, then there exists some n such that B to the n is in A. So it's sort of like being a prime ideal, except it's a little weaker. So instead of like if A is not in the ideal, then B must be in the ideal. B itself need not be in the ideal, but some power of B needs to be in the ideal. So certainly prime ideals are primary because you always have n equals 1. But in general, you can have primary ideals which are not prime. I don't know any examples off the top of my head, but I know that they must exist, because if they didn't, then primary wouldn't have its own name. It would just be prime. Alright, so we start out with a problem which you haven't seen because I don't think I've done this problem. Well, I certainly haven't at this point. I don't know if I will. But basically, it turns out oh wait, no, I think maybe I proved this one in the lectures. That if you take the ring of fractions of p to the n, then this is the ideal. Yeah, I did this in lectures. So if you take the ring of fractions of a ring, that's the same as the ideal generated by the image under this natural map of that ring. And here, of course, this is defined to be Qn. Okay, so this is equal to this. Basically, we're going to want to get to like a particular equality that we'll do later on in like the third paragraph. But until then, we're just proving some like preliminary facts. All right, so this equals this, so that's good. Next, I claim that if you take the radical of this is equal to the ring of fractions of this radical. So of course here, the radical, this is the radical of the ideal A. This is just all things of the form A to the n, where A is in A, and R is in, no, N is in natural numbers. Of course, not including 0. Well, 1 is, no. Yeah, it's definitely not including 0. Oh, my laptop is getting really hot. Anyways, so I claim that this equality, and how do you prove equality of sets? You prove by inclusion. So first, suppose we have an element here, we'll prove it's in here. So take an element A over S and S inverse R of P to the N. This means that S is in S and A is in R of P to the N. So since A is in this set, there is some M, such that A to the M is in this ring. Now, S to the M is going to be an S by closure under multiplication. And so if you take this fraction and raise it to the M, you get A to the M over S to the M, which is an S inverse P to the N. So therefore there exists some m such that this raised to the power of m is in here. That's what it means for this fraction inside the parentheses to belong to the radical, just using the definition. Therefore we have inclusion in the one direction, because any element of here is in here. So for the other direction, suppose you have a fraction in this radical. This means that there's some m such that raising a over s to that power gives you a to the m over... Ooh, what is going on here? Oh, wait. Yeah, what? I don't know what I'm... Ooh, oh, man. What am I doing here? Okay, so... This should be... No. Okay, so yeah, this should be a over s to the m is a to the m over s to the m, which is in that set. Yeah, that's what it means to be in there. I don't know why. Not only did I get it wrong, and get it wrong twice in a row, but I got it wrong with like different letters. So I don't know what I was doing when I wrote this. Anyways, so this means the fact that these are all equal. Okay, so a over s to the m is in here. So a to the m over s to the m is in here. So that means that a to the m over s to the m is equivalent to some element in here, i.e. there is some b in this ring and t in here such that this fraction is equivalent to this. Now that I'm looking at this, what I should have done is I should have flipped these two around, because what we're doing is we know, because a over s is in here, we know to begin with that this thing, this raised to the power, is in here, but then we're writing this like this so that we can work with this. So anyways, so when we start this equation here, we don't know that this is in here. But we learn that this is in here by showing that this is equal to this and using the fact that we know that this is in here. So sort of poor writing on my part. Yeah, this small bit is just a mess here. Anyways, so we have some element in here and some here such that these two are equivalent. What does it mean for them to be equivalent? That means there's some u in s such that this thing is 0. So move this to the other side and distribute it. Now choose some k just bigger than the maximum exponent of n and m. And then what we can do is when you take uta raised to the k, then you can write it like this. And now here a to the n, where's a to the n? Where's a? Where's anything? Okay, let me think about this. Let me think about where everything is. We don't really know. Okay. What we want to do is we want to prove that UTA, we want UTA to be in the radical of p to the n, i.e. we want to take UTA, raise it to some power, and prove that it's in p to the n. What do we know is in p to the n? The only thing we know that's in p to the n is b. So maybe I'm looking at the wrong thing here. Maybe it shouldn't be UTA that we're using here, but rather USB. Yeah! And what we're going to do is we're going to use... Okay, so... Here's what we're going to do. B is in p to the n. So, Okay, we're going to... I'm going to do this on the fly, and I'm probably going to mess it up. Okay, so... if we take us to the mb and raise it to the power of n, then this is u to the n times s to the m plus n times b to the n. And b to the n, we know is in p. No, wait. No. Okay. We know that b is in p to the n. So USMB is in p to the n, so UTA to the m is in p to the n already. So what am I doing? What do I want here? I want UTA to be in R p to the n. Okay. So what if we take... Oh, okay. So if you... Okay. If we take UTA and raise it to the power of m... Okay, yeah, this is what we did when I learned this, when I was going through this. Okay. So we're going to get rid of this. So UTA to the m is going to equal u to the m minus 1, t to the m minus 1 times UTA to the m, which is going to be in p to the n. Okay? So therefore, UTA belongs to the radical of p to the n. So this thing, thus UTA belongs to the radical of p to the n. That's not because of whatever junk I wrote here. It's because of this thing. Okay? So therefore, since UT and S are in S, the product is as well. Okay, so you take A over S and you multiply on the top and bottom by U over T. Or by U times T. So then you get UTA on top and UTS on the bottom. UTA, we just proved, is in the radical of p to the n. And UTS we know is in S. So this fraction is in S inverse radical of p to the n. So we've taken this element, which we started in this radical and proven it's in here, and so then this is in here, i.e. we have this containment, and that's exactly the reverse containment that we wanted, and so we get equality. Alright, so that finishes the first paragraph of this proof. Okay, the next thing I want, the radical of p to the n is equal to p. Certainly p is contained in this radical because any element of p is contained in p to the n, because it's just, you take the element and you... Oh wait, is that obvious? It should be. Well, I guess not, because prime ideals don't have one in them, because if they have one, it's the whole thing. Oh, no, of course. Ooh, wait. Yeah, no, wait. Okay, p is contained in the radical of p to the n. The radical of p to the n is the collection of all elements. Oh yeah, this is easy, because you take any element of p, take like a pi. If pi is in p, then pi raised to the n is in p to the n. So there is a power of pi, which is contained in p to the n. Therefore, pi is contained in the radical. Okay, so yeah, this is clear. Alright, so next, let's say we have two ideals, A and B, and A is contained in B. Then the radical of A is contained in the radical of B, because if you have this, then there is an element A. No. What am I doing here? So if A is contained in B, then for all A in RA, so if you get, this holds because, okay, I'm just going to cross this all out. Okay, so let's say you have an element in, so let's say we have an A, let's say we have an element x in R of A, then this means that there exists an element A in A and an element n in the natural numbers such that a to the n equal, a to the n is in A, but this is contained in B, and so therefore, since there is a power of n such that a to the n is in B, this means that a is contained in the radical of B. Okay, so I guess it's really, that part was good. So it's this a, this part here should be replaced with this part. Yeah. So, yeah, I don't know. Oh, wait. So x equals a to the n. Okay, wait, so a is in R of B. And since ideals are closed under multiplication, x equals a to the n is in R of B. Okay. So yeah, this is just a huge mess. This is just a complete mess. But anyways, so this holds because if you have an element x in the radical of A, then there is some a and some n, such that you can write x as a to the n, where a to the n is in this ideal here. That's what it means to be in the radical. Right? Because the radical is all things of the form a to the n, where a is an a and n is an n. So x equals a to the n for this, but a is contained in B, so x is contained in, or so a to the n is contained in B, which means that a is contained in the radical. And since ideals are closed under multiplication, raising a to the power of n keeps it in the radical, but then x is precisely a to the n. Okay, so therefore, x is in the radical of B, and this holds for any x in the radical of A. Therefore, radical of A is contained in the radical of B. Okay. Next, p to the n is contained in P, because if you have any product in p to the n, then by primeness, some pi must be contained in P, and then the entire product is contained in P because it's an ideal. Idealness. Nice. Alright, so... Okay, so combining that with R of A, with A contained in B implies R of A contained in R of B, P to the n contained in P implies R P to the n is contained in RP, but now RP is equal to P. Clearly P is contained in R of P. That's just a specific case of this inclusion right here. And then, for the other inclusion, if you have an element P in the radical, then this means that there's some m's such that P to the m is in... P to the m is in P. What? Oh. Yeah. Primeness again. Okay, so let's see here. Certainly P is contained in R of P. Now take any element in R of P, call it P. That means that there's some m such that P raised to the power of m is in P, but P is a prime ideal, so that means that some factor in here must be contained in P, but the only factors in here are P, so P must be contained in there. Alright? So yeah. And then, what else? Okay, so that's equality. And then, so therefore, R P to the n is contained in P. And so these two are equal. So, Rp to the n is contained in R of p, which equals p. Therefore, Rp to the n is contained in p, and that was the other inclusion, and so we have equality. Alright, let's finally wrap this up. Okay, so all of that work was to prove these few equality signs. R of Qn is equal to R of S inverse P to the n. That was the first thing we said. That's using the problem from the other exercise set that I probably won't put up, or maybe I will, who knows. Then we have this equality here from the first paragraph. Then we have this equality here from the second paragraph because R of P to the n is equal to P. Therefore, S inverse of that equals S inverse of that. We also know that S inverse P is the unique maximal ideal in this localized ring because this is a local ring. And we know that you localize it a prime ideal and you get a local ring, and the unique maximal ideal is given by S inverse P, where P is the prime ideal you localize at. Okay, so then we use problem 2 of this problem set, which is another thing that I may or may not put up, but what that says is that if the radical... What does it say? If the radical of an ideal is maximal, then the ideal is primary. Yeah. So Qn is our ideal. If the radical of an ideal is maximal, then the ideal is primary. Since the radical of Q to the n is maximal, Qn is primary. So since Qn is primary, suppose... Okay, so now we know Q to the Qn is primary, so now let's prove that phi inverse Qn is primary. So suppose AB, this product is in this phi inverse Qn, and suppose A is not in phi inverse Qn. We want to prove that some power of B is in phi inverse Qn. So AB is in phi inverse Qn. That means that the image of AB is in Qn, but the image of AB is just AB over 1, which we can write as A over 1 times B over 1. This is in Qn. And A not being in phi inverse Qn means that A over 1 is not in Qn. So since Qn is primary, and AB over 1 is in there, or this product is in there, and this term is not in there, then some power of B over 1 is in Qn. So there, i.e. there is some m such that b over 1 to the m is in Qn, but this is just b to the m over 1, which is in Qn. But this is precisely the image under phi of b to the m. So that means that b to the m is in phi inverse Qn. So if AB is in phi inverse Qn and A is not in phi inverse Qn, then there's some m such that b to the m is in phi inverse Qn. That's what it means for phi inverse Qn to be primary. And that's what we wanted to prove. We wanted to prove that phi inverse Qn is primary, and we've done it, so we're done. Whew.